The following example will help you consolidate your understanding of expectation values in quantum mechanics. It will also highlight an important phenomenon, the existence of the so-called zero-point energy in oscillatory motion. Let us revisit a system we have touched upon previously in this course, a particle of mass m performing one-dimensional harmonic oscillations with frequency omega. We'll start by considering the classical mechanical version of this system. Previously, we have looked at the scenario in which the system is characterized by the following trajectory. The time-dependent position of the oscillating particle, x of t, is given by its initial position, x sub 0, multiplied by the cosine of omega t. The particle's momentum equals the mass multiplied by the time derivative of the particle's position. Its potential energy is half the spring constant, m omega squared, times the square of the position. Kinetic energy equals the square of the momentum divided by twice the mass. And, finally, the total energy of the system is the sum of its kinetic and potential energies and equals half of m omega squared, times the square of the initial position. Let's observe two things here. Firstly, the total energy is time independent. This is a manifestation of energy conservation in this system. Secondly, the total energy can, in principle, take any non-negative value. In particular, the total energy is zero if the particle rests at the equilibrium point, that is, if x sub 0 equals 0. Now, let's look at the quantum mechanical version of this system for the particular scenario when the oscillating particle is in a coherent state. We have already derived the corresponding coherent state wave function. It is given by this expression. As a reminder, alpha in this expression stands for m omega over 2 h bar. When performed on an individual quantum oscillator, measurements of the particle's position, momentum, potential, kinetic or total energy will generally return random, unpredictable results, distributed in accordance with the corresponding probability distributions. Nevertheless, the expectation values of these measurements are well predictable, and we know how to calculate them. The expectation value of position, mean x, is given by the integral of x sandwiched between psi and psi star. Calculating this integral, as well as all subsequent integrals in this lesson, is left as an exercise. But don't worry, should you encounter any difficulties performing these calculations, you can always consult the detailed solutions accompanying this lesson. So, the integral for mean x yields x sub 0 multiplied by the cosine of omega t. Note that this result coincides with the expression for the time-dependent position of the corresponding classical particle. The expectation value of the particle's momentum is given by the integral of the momentum operator, sandwiched between psi on the right and psi star on the left. Calculating this integral, you will get minus m omega x sub 0, multiplied by the sine of omega t. Of course, this is the same expression as the one for the momentum of the corresponding classical particle. So far, we haven't seen any differences between the quantum mechanical expectation values and the corresponding classical quantities. One might think naively that the quantum system is essentially equivalent to the classical one, provided we replace all classical quantities with the corresponding expectation values. This is, however, not true. Differences between the quantum and classical oscillators come to light if we calculate the expectation values of the particle's potential, kinetic and total energy. For the potential energy, we have this integral. Evaluating it, we obtain the following expression. We have two terms here. The first term coincides with the classical mechanical expression for the potential energy of the particle. The second term, however, h bar omega over 4, is new. It is time independent and has h bar in it. You can view it as a quantum mechanical correction to the classical energy. It is relatively insignificant when the classical potential energy of the particle is large, but it becomes dominant at low energies. The expectation value of the kinetic energy is given by the integral of the corresponding differential operator, sandwiched between psi on the right and psi star on the left. Doing this integral, you will obtain the following expression. Again, this is the sum of the kinetic energy of the corresponding classical particle, and the same quantum mechanical correction, h bar omega over 4. Finally, the expectation value of the total energy is the sum of the expectation values of the kinetic and potential energies. Once again, it's a sum of two terms. The first term, half m omega squared times x sub 0 squared, is just the total energy of the classical harmonic oscillator. As I've already mentioned, it can take any value from 0 to infinity. The second term, h bar omega over 2, is a fixed amount of energy entirely determined by the oscillator frequency. So, the total energy of the quantum oscillator is always greater than or equal to h bar omega over 2. This minimal amount of total energy, always contained in the quantum mechanical oscillator, is called the zero-point energy. The existence of zero-point energy signifies an important difference between classical and quantum oscillations. Unlike its classical counterpart, a quantum oscillator cannot be completely at rest. Its motion cannot be frozen out. There is always some amount of vibration present. The presence of zero-point energy in quantum harmonic motion can be understood from the standpoint of the so-called Heisenberg uncertainty principle, a concept we'll explore later in this course.